So we perform one of these tests, and now the question is, what does the result look like? So we're going to talk about a stress-strain curve here. So I'm going to draw some really big axes here because we're going to draw lots of pictures on this. So there's my y-axis. Here is my x-axis. You guys can see that okay, good. And this guy down here is going to be strain, and this is going to be stress. Okay, so when we perform one of these tests, what we're going to do is take our material, put it in the machine, and we're going to pull on it at a certain displacement rate. So we're going to control the amount of strain that we put on the material, and we're going to measure what stress we're using to create that strain. So we're essentially going to go along this axis. We're going to track along this axis. And that's going to be called displacement controlled testing. And it's nice because when we do it that way, we can get the full stress strain curve, including all the fun inelastic parts. So first off, we're going to put the part of the stress strain curve we've been talking about so far. So I can start here at 0. We have 0 strain, we have 0 stress, and then I can draw a straight line. And of course, we've been talking about this now in class. We know that this is the elastic modulus E, and I'm going to draw that up to a certain point here, and that point I'm going to call the proportional limit. Okay, and at the proportional limit, of course, we are no longer able to use our nice relationship of the elastic modulus. So up until the proportional limit, we're okay, we're good. We can use the elastic modulus to relate strain to stress. After that, you'll see we have some issues. So the first thing that happens is we're going to start to curl over here, and at a very small amount of strain later, we're going to get to another point which we call the elastic limit. And sometimes people don't really distinguish between these two, but in this class for right now, we're going to make a distinction there. So we're still able to return back to the origin at the elastic limit, but because there's a slight change in the slope, we can no longer say that the stress and strain are related by this proportionality constant, which is the elastic modulus. So there's a slight difference here, but it's not very large. After the elastic limit, we end up entering the yield plateau for steel. So when that happens, we end up drawing a straight line across, and I'm going to draw a line over this way in light green so you can see what that looks like over here. We're going to call that the yield stress. So I'm going to write that over here. This is the yield stress. And some interesting things happen once you reach that yield stress. Let's first imagine that we unload our specimen. So we come all the way up past the proportional limit, past the elastic limit. We come up to this point here, and now we decide that we want to let go of our specimen. So we now reverse our machine and we drop the strain down this way. What you're going to find out, and I'll see if I can draw this as best as I can, what's going to happen is instead of going back this way and back down to the origin, you're going to come down this light green line down to this point here. And what you'll find is that now you have some amount of what we call residual strain. And what does that mean? It just means that we didn't come back to where we started. So we have some strain that remains in our specimen even after we unload it to 0 stress. And so that's what we're talking about when we talk about residual strain. I should probably make a few more points here. Let's draw a couple more pictures. So in this region here, now that I have this, I can start to draw it. What we're doing, just to remind ourselves, is we have a rod and we're pulling on it with some force P. The rod has some area A, and we are measuring some delta in that length. So we say it's L0, and we're measuring some delta L. So now I can actually go back. I should have done this to begin with, so I apologize. These are our axes. So epsilon here, we've defined this as delta L over L0. That's what we've done in the past. And I'm going to say that now we can talk about it in a little bit more detail. This is what we call the engineering strain. And it's based on the original length of the material. That's important. Stress up here, this is going to be P over A, and I should really say A naught. And because that's the original area there, we can call this the engineering stress. And it's important that I point that out because the picture that I'm drawing here is relating engineering stress and engineering strain. And there's some different ways you could express this which would change the way this picture looks. Okay, so I apologize. Let's go back to our picture here. So we had come up to this point. We had unloaded back to 0. So I'm trying to draw some arrows here that says we're unloading back to here. And the next question you might ask yourself is, what happens now? We start here. What happens if I reload the specimen? So now I start to pull the sample apart again. What's going to happen to my curve? And what you'll see, if now I'll follow this blue line, I'll start at that point and I'll go up on the blue line. Now the green and the blue line are really the same line, but I drew them next to each other just so that you could see those. And I think I even drew them kind of close to Seahawks colors. It's a little bit lighter blue, but you get the idea. So now I'm back on my curve, and what's going to happen is I might go a little bit further on my yield plateau. That's this region here. And then you'll start to see what we call strain hardening. So now the stress is going to go back up, and it's going to come up to some point here. And that point there, I might have drawn it a little too high, but this is going to be our peak stress, and we're going to call that the ultimate stress. So ultimate stress. So this is the largest stress that the material can sustain. We call this region here, this is the strain hardening region. And so the fact that we start to get more stress for more strain after the yield plateau is what we consider hardening in this case. And the interesting thing is, of course, if you come back down now, you would come back along an elastic line as well, and you'd come back up to this point before you'd continue on the curve. So after, let's go back to our picture here. So we started with some original area, we had a load on there, we had some original length, and then we had a change in length. We've come up, we've gone past the proportional limit, past the elastic limit, through the yield plateau, and in this region here, we still have something that looks a lot like a cylinder. It's a little bit longer. We still have a load on it. The load is now higher, so P is going to be a little bit higher. We still have some area now. Might be a little bit smaller than it was to start, remember, because of Poisson's ratio. And it's going to be a little bit longer. Now, something very curious happens after the ultimate stress, and that is the stress for increasing strain starts to come back down. And then it starts to fail, and eventually it fractures. So that right there is going to be fracture. And that seems rather strange. We're actually going to break at a lower stress than the material could achieve. And that's should be somewhat curious, because you'd imagine if this thing's going to fail, it should fail at the maximum stress, right? Well, in fact, it actually does, but it has to do with the fact that we're in engineering strain and engineering stress. So what happens is once we get past ultimate, we start to have what we call necking in the material. So now the material starts to look more like an hourglass here. And because of that, when we apply some load on it, the area here is not the original area anymore, it's some area 1, which is a lot smaller. We're getting this plastic flow. We start to have a smaller, reduced area in the middle of our section. We start to neck, which is what this picture is trying to describe. And when that happens, we actually have a much larger stress. So that is what we call true stress. And the true stress diagram, if I could draw it, it would be off the page in this case, so I will do that. It's going to come up, it's going to follow this line for the most part, but then at some point it's going to diverge, and it's going to keep going up, 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 off the page until fracture. So this up here would be our true stress diagram. And what we mean by true stress now is this true stress is going to be the load divided by the current area, A1. And so in that case, the fracture will occur at the peak of our true stress, true strain, or engineering strain diagram. And so that, I should write necking here. This is going to be the idea of necking. And so this is typically what we would see if we were to go to a machine and we would test our sample in that machine. So we'd see a curve that looks something like this. It's not drawn to scale. I'll put some pictures of what this actually looks like. I wanted to exaggerate this elastic portion so you could see it. But certainly this is probably the most important kind of concept or picture. We have some yield plateau, we strain harden up to some ultimate stress, and then we have a fracture. So we might have some different strains here. We might call the strain at yield the yield strain. We might have a strain at the start of strain hardening. We might have a strain at the ultimate stress, which would be here. And those would be some ways that we could characterize the nonlinear behavior of this material.